When physicists talk about mass, they're normally referring to one of two things: gravitational mass, the one that causes weight, or inertial mass, the one that makes things hard to push. In classical mechanics, it's not obvious that these two quantities always have to be the same, but in our experience, they are.
That's another dent.
If a thing has a half a kilogram of mass, that means that it has both a half a kilogram of gravitational mass and a half a kilogram of inertial mass. And from the first time that some early human ancestor picked up a rock and felt what it was like to wave something heavy around, until 1915, the reason that these two quantities were the same was a mystery. If I wanted to accelerate an object sideways, I would need to apply a force. And the more massive that object, the larger the force I would need to apply to accelerate it at the same rate. That's inertia. And when I put one of these masses on the scale, test mass A, we see that test mass A weighs 5 newtons. Now, if the scale were to exert more force than the object's weight, say 6 newtons, the object accelerates upwards. Shocking, I know. Now, it's actually fairly difficult to lift with exactly 1 extra newton of force, so here that is again in slow motion when I got a little bit closer to exactly 6 newtons. It's worth noting that while I'm pushing up with more force than the object's weight, the object isn't just moving upwards, it's actually accelerating upwards. Its vertical velocity is increasing the whole time. Inertia is like a resistance to acceleration, but you need to be careful with how you apply it. Here we have two people separated by a distance of 1 meter, and then, for some reason, the distance between them increases to 1.5 meters. Clearly one of them accelerated, but who? Okay, that's kind of obvious, it's the one on the left. But what if I take away the background cues? Okay, maybe it's still obviously the one on the left. But now, what if I also accelerate the camera? Is it less obvious? The one on the right experiences a coordinate or spatial acceleration, visibly moving within our reference frame. But we can see from the pendulum that the one on the left, despite apparently standing still, is experiencing an acceleration. And we call this a proper acceleration. In the absence of any context, physics relies on the local experience of an observer to answer the question of who's accelerating. And if the coordinate acceleration, the visible motion of stuff, lines up with the proper acceleration, the forces and acceleration experienced by those objects, then we say that we're in an inertial reference frame, because inertia works properly in this reference frame. The trick is figuring out where you need to put your camera so that you know that you're seeing an inertial reference frame and not one of the weird accelerating reference frames. Here I have a camera pointed at a marble in a box. At a certain moment, I'm going to turn on a fictitious force and pull the ball to one side. Olimar clearly knows what's about to happen. And there, the ball suddenly accelerates to one side of the box and bounces lethargically against the wall. Isn't that incredible? The ball moved sideways! Okay, now before we designate this the most boring physics demo of all time, let's look at that again from a different perspective. From above, this is what actually happened. The box was just traveling in a straight line and then suddenly started accelerating into a circular path. The ball in the box basically just kept going in a straight line, but from an observer inside the box, it looked like it was pulled by an unseen and inexplicable force. Look at the motion of the ball carefully, and the only real force that ever acts on the ball was the force applied to the ball by the wall of the box after the ball bounced. And that force actually points towards me in this demo, the center of rotation. There is no force that makes the ball move towards the wall of the box. It just has inertia, and it's moving in a straight line because that's how inertia works. An object in motion will remain in motion unless acted upon by an external force. Of course, in this real-world example, there's actually a small deviation because of friction with the floor of the box causes the ball to divert upwards slightly, and it loses some translational kinetic energy into rotational kinetic energy, but it's extremely close. From inside the box, it only looks like the ball is experiencing a sideways force because the whole reference frame is accelerating. But what does this have to do with gravity? Well, we're in the box. This marble is not accelerating towards the ground. Everything else, me, the ground, the table, the camera, is accelerating upwards right now at about 10 meters per second per second. Bear with me. Gravity, the nice, friendly, Newtonian, classical gravity that we all know and love, is a fictitious force. This is what gravity looks like in the reference frame of Earth's surface. Stuff falls. This is what we're used to. Now let's zoom out to a true inertial reference frame, and this is what gravity looks like. The beanbag is just either not moving or moving at a constant rate, and suddenly the ground comes up and slams into it. How rude. I also need to point out that intentionally putting the most expensive objects that I own into free fall repeatedly was terrifying.
Don't like this at all.
When you are free falling in a gravity field, that is actually an inertial reference frame, like a skydiver in a vacuum. And any acceleration within this frame must be felt as a force. It's pretty hard to see in this case because your brain takes cues from the background and you know the camera is falling. So here, if I remove the background, you can see that after the beanbag is released, my hand accelerates upwards, propelled from the force on my feet and transmitted through my body. Then we're just looking at a beanbag at rest in an inertial frame. Nothing weird about that. And then the table comes along to accelerate the beanbag within the inertial reference frame. It's kind of a bizarre way to think about it. If you want an example to compare to, think about this sideways, so we don't have to care about gravity. The object is at rest, and then a force is applied that causes it to accelerate. In this particular case, it's the normal force that the ground exerts on the object that's doing the true acceleration, accelerating the beanbag upwards, away from Earth's surface.
Comparing to the centrifuge example, the only real force applied to the object, the only force that results in a proper acceleration, is when the object hits a surface. In both the centrifuge case and the gravity case, when the object starts moving in the local reference frame, it's because of a fictitious force. And therefore, when that object eventually hits something, and that something else applies the force that keeps the object in the accelerating frame, it's actually in the opposite direction. This bounce, or the force of the floor or the wall here, is what actually keeps the object in the accelerating reference frame. So kind of by definition, it has to be opposite the fictitious force that's trying to get the object to leave the reference frame.
I think this is a really difficult thing to grasp because our human brains are hardwired to exist at 1G. We always feel like we are being accelerated, pushed through our feet upwards at 10 meters per second per second. And that's not weird, because it's what we're used to. So here's a way that you might be able to train yourself to feel this acceleration. When you stand just on the ground, there is a force on the bottom of your feet. You don't notice it, but you can feel there is physically a force on the bottom of your feet. If you sit down, your feet no longer feel that force. In fact, if you've been standing for a while and you sit down, you might even feel your foot like swell out. Your feet are getting less compressed, just like that spring scale. Now, if you lay sideways, you can experience the same force on your feet, say, if someone pushed you, accelerating you sideways through our customary reference frame here on Earth's surface. That force on your feet causes you to accelerate, always. Causes you to accelerate, always. The real kicker here is that when you're standing up and you feel that force on your feet, it's also causing you to accelerate in an inertial reference frame. This is why inertial mass and gravitational mass are the same thing. If I wanted to accelerate an object sideways, I would need to apply a force. And the more massive that object, the larger the force I would need to apply to accelerate it at the same rate. That's inertia. In our falling reference frame, the weight of an object is the force necessary to keep that object pinned to Earth's surface. In this reference frame, the object must be continually accelerated, and more massive objects require more force to accelerate them at the rate of gravity. In the lab frame, that means that they look heavier. We see there's an initial large force at impact, but once that settles, it's measuring the weight of the object. This is the force necessary to continuously accelerate an object within an inertial reference frame at about 10 meters per second, or 1G.